Hey guys, how you doing? This is Coach Scott with Purple Wave Chemistry, and hey, let's go more into Unit 3 a little bit. Let's start talking about the electronic configurations for the whole periodic table. All right, take it for what we learned last episode. So, we talked about the main group configurations, right? So, depending upon the electronic configuration for all the periods of the table, let's get a little bit further, a little bit more, and things get a little bit more complicated when we start talking about the transition metals, right? So the first three periods, or the first three rows, you're only dealing with s's and p orbitals, right? Now as we go further down, we're going to add the d orbitals and the f orbitals, but we're still doing the same thing for determining electron configuration. It's the same. And when we use shorthand notation, it makes it a little bit easier. Don't have to write as much. Okay, so, ooh, that's a real crooked little fall there, but that works. So this is how the electrons fill orbitals. Let's look at period 4. And I think I told you in your guys' periodic tables, I would write N for the energy level. And then I'd write N minus 1 because notice that this goes from the fourth level, so the fourth row. This becomes the 3Ds, N minus 1. And when you go to 6, okay, these go right there. So on 6, I would write N minus 2 on the actinides and lantanides, or vice versa. Okay, 4 and 5. So, to find the configuration for like titanium, right, we're going to go up all the way over to the noble gases, and the noble gas above titanium is argon. So write your argon in brackets, then start counting. 4s1, 4s2, 3d1, 3d2. There you go. That's it. You just wrote it. So it's argon, 4s2, 3d2. So titanium, we're only going to have valence electrons that are s's or p's right now. Titanium only has two outer electrons, these two in the 4s level. These are the ones that are furthest from the nucleus. The two electrons in the d orbital, they're closer to the nucleus because they're at n equals 3. They're inside that outer layer. D and f orbitals are never valence electrons. All right. So throughout the main group, the number of valence electrons equal the unit digits of the group number 1, 2, 13, 14, 15. All right. So this is in group 12. All right. But there are two valence electrons. Now there are some exceptions, and well, you might talk about them later. Let's look at germanium. Okay, germanium. Argon, 4s2, 3d10, 4p2. Let's see if I'm right. I am. So the configuration is 4 argon, 4s2, 3d10, 4p2. Now there are only 4 valence electrons, 4s2 and 4p2. You still got the 3d10s in there, but you've only got 4 valence electrons. Let's look at arsenic. Argon, 4s2, 3d10, 4p3. Again, y'all see a pattern now, right? We've got this. Now, when we go up to period 5, same principle. Let's look at 10, SN. Go up, krypton, right? 5, 5s2, 4d10, 5p2. There's a pattern. All right. Now, when you get to 6 or 7, 6 and 7, 6 and 7, all right, there are hidden blocks. That's what the F's are. They're hidden within the D block. Okay. there's 14 elements that are in period 6 between 56 and 72. They are normally below it, right? In period 7, there's another 14 elements between 60, 88, and 104. Again, they're at the bottom, all right? So this next slide, and I gave you a copy of this, this is how the periodic table, push them in there, and that's the way it should look, okay? That's the way it should look. Pull them out, because this would be a very long periodic table, and then we don't want to do that, right? But you have to count them. So, if I'm looking for lead, PB, I go up, and I'm writing my configuration. I'm going to write xenon, right, XE, block, 6S2, 4F14, 5D10, 6P2. So you got 4 valence electrons. There you go with the configuration. And there you go. So when you have the standard periodic table, don't forget you have to go down here when you're on the 6th level. Alright, now let's talk real quick about stability. Alright, elements want to be stable. Alright, they really, some are more reactive than others, others not as reactive. So the ones that are not reactive, we call those stable. They don't change easily. Alright, and when you group them together, you see a pattern in the periodic table. Alright, so number 1, if you've got a full energy level, i.e. the inert gases, noble gases, they're happy, very stable. The next is when you have a full sublevel, like the D's, a full D, or the S's, or the F's, they're happy. Alright, they're happy. See them right there. The last one is when you have a half full sublevel, like the 5D or the D5s or the F7s. They're not as stable as with like the full energy level or the sublevels, but they're pretty happy about life, right? There are some exceptions. You're not going to study them in AP chemistry. You really don't need to know. All right. We're going to pretty much focus on main group elements, and we're not really looking for the exceptions. Just follow the rules of naming, you'll be fine. Okay. Well, that's pretty much on the periodic table. Our next videos or two is going to be about periodicity and the different types and what's controlling periodicity. Pretty much the Coulomb's law and Zeph and distances from the nucleus. So anyway, this is Coach Scott saying how a balloon can connect, and have a great evening.